This video is on Chapter 9, Section 9.6, the pH scale. So the pH is a value, a simple 1 to 2 digit number with decimals that allows you to classify solutions as acidic, neutral, or basic without having to look at the molarity of the hydronium ion, the H3O plus ion. It's an easier way to look at the acidity or basicity of a solution. And you obtain the pH value by using the formula here that says pH equals negative log of the concentration of H3O plus. This log is the logarithmic function of base 10. The way the logarithmic function is that the lower the pH, the higher the concentration of H3O plus. If you have a concentration of H3O plus that is greater than 1/10 to the negative 7 molar, this will translate into a pH that is less than 7, because the pH is equal to when your coefficient in the concentration is 1, the pH is equal to the exponent. So when you have, for example, 1/10 to the negative 2, the pH will be 2. If the concentration is 1/10 to the negative 5, then the pH will be 5. And so when pH is less than 7, this corresponds to acidic solutions, right? Remember that acidic solutions contains more hydronium ion than hydroxide ion. A neutral solution will be for a pH equals 7, and that's when the concentration of the hydronium ion is 1/10 to the negative 7 exactly. And a basic solution is when pH is above 7, and that translates into concentration of H3O plus being smaller than 1/10 to the negative 7. Remember that for this concentration to be less than 1/10 to the negative 7, it means you have concentration with 10 to the negative exponents with exponents greater than negative 7, like negative 9, negative 10, negative 12. And so the pH then is going to be 9, 10, or 12, and it's above 7. And that corresponds to a basic solution. A basic solution has fewer hydronium ion, H3O plus ions, and has a lot more OH minus ions, the hydroxide ion. So notice here that when you are going down by 1 unit in the pH value, let's say, for example, pH 3, and you go down to pH 2, this will translate into a concentration of H3O plus multiplied by 10. There is 10 times more H3O plus ions in pH equals 2 than pH equals 3. So the pH scale goes from 0 to 14, 7 being in the middle and representing the neutral solutions. When you go down from 7 to go down in pH, the acidity increases, and when you go up in pH from 7 to 14, the basicity increases. And as I said, a difference in a pH unit of 1 going down represents 10 times more hydronium ions in solution than the previous solution. So you've encountered, in your life, you encounter solutions that are acidic and basic. And for example, fruits are all acidic, lemon being the most acidic of all with a pH of 2.3. Strawberries, tomatoes, all fruits are acidic. You can see here milk is represented in the middle, and it's almost neutral, but not quite. 6.5 is the pH for a whole milk, and here we're talking about cow's milk. And on the side of the basic side, all the detergents you find in your home tend to be basic, like bleach with a pH of 12, ammonia with a pH of 11. Philips, I think, is a brand of anti-acid pills. So all of these are basic. Any kind of cleaning agent tend to be basic. And in your body, you have also fluids, and they have a pH value. And depending on where the fluids is from, it will have a different pH value. Starting from saliva, which has a pH of 5.8 to 7.1. Going down into the stomach, the pH will decrease a lot down to 1.6 to 1.8. And that's because we are secreting hydrochloric acid in the stomach. To have a proper digestion, you need an acidic pH in the stomach to start digestion of proteins in particular. Pancreas is secreting fluids with pH 7.5 to 8.8. Small intestine pH is 8.5 exactly, or around. Large intestine pH is going from 5 to 7, depends on what you have eaten. And urine, again, depends on what you have eaten, but pH can range from 4.6 to 8. And then finally, blood. Blood has a very narrowly maintained pH at 7.4. It can go from 7.35 to 7.45, but that's the widest range that would be comfortable for your health. So blood has to be maintained into that pH. So this is practice problem 9. If you look at your list of practice problems found in chapter 9, section 9.6, the pH scale, you will see number 9 is this slide. And it's asking you to identify each solution as acidic, basic, or neutral. You can pause and think about it before listening to what comes now. So HCl with a pH of 1.5 is acidic. That's acidic because the pH is below 7, right? And if you look at the formula of HCl, it starts with an H as first in the formula, so you know it's an acid. Pancreatic fluid with a concentration of H3O plus equals to 110 to the negative 8 molar. If you look at this value, so you need to remember that you need to compare the hydronium ion concentration to the value of 110 to the negative 7 molar. That's the reference for a neutral solution. So 110 to the negative 8 is smaller than 110 to the negative 7. Remember that when you have negative exponent, it means here that you divide 1 8 times by 10. So this is smaller than dividing 1 7 times by 10. If H3O plus is smaller, that means OH minus, the hydroxide ion, will have a greater concentration. And that tells you it's a basic solution, because basic solutions have more OH minus ions than H3O plus ions. C, a soft drink with pH equals 3.0. That's acidic. We know because pH below 7 is acidic. Soft drinks tend to have phosphoric acid in them or carbonic acid. So they usually are acidic. D, pH equals 7.0. That's exactly a neutral pH. pH to be neutral, or a solution to be considered neutral, has to have a pH of exactly 7.0 or even more zeros. It cannot have any other decimals than zeros after the 7. Like, for example, 6.95 is not a neutral pH by definition. So E, the hydroxide ion concentration, OH minus, equals 3 times 10 to the negative 10 molar. So again, you need to compare this concentration to 1 10 to the negative 7 molar. We divide 3 10 times by 10 compared to 1 divided 7 times by 10. That's that OH minus concentration is smaller than 1 10 to the negative 7. So if it's smaller, that means you have more H3O plus ions than OH minus ions, and more H3O plus ions means it's acidic. F, H3O plus concentration of 5 times 10 to the negative 12 molar. Again, compare this to 1 10 to the negative 7 molar. 5 10 to the negative 12 molar is a smaller value than 1 10 to the negative 7. So that means the concentration of H3O plus is small and the concentration of OH minus is large. And that indicates a basic solution. Okay, now you will need to be able to calculate the pH using your calculator. First, a word about determining the number of significant figures in the pH value. There is a reminder of this rule in your yellow reference packet, page 5, that is dedicated to chapter 9, acids and bases. On that page 5 of your yellow packet, you will see a note that says that the hydronium ion concentration should have the same number of sig figs as there are decimal places in the pH, which means digits to the right of the decimal point, and vice versa. And so this is also said here as the number of decimal places. So for the pH, only decimal places matter as far as precision that you need to keep. So it's the number of decimal places in the pH that must be the same as the number of significant figures in the coefficient of the concentration of H3O plus. In the example below, the concentration of H3O plus is 1.0 times 10 to the negative 2. If you look at the number of sig figs in that concentration, it's 1 and a 0, 2 sig figs. This should translate into a pH with 2 decimal places. And so pH, when you have a concentration of that value, pH is equal to, and the 2 here comes from the exponent in your concentration. And then we need to keep 2 zeros because we need to see 2 decimal places due to the fact that the concentration had 2 significant figures. Remember that the decimal places mean digit to the right of the decimal point. So let's practice this and enter in your calculator, try to calculate the pH of 1 10 to the negative 7. So the negative sign that you put in front of the log function is the one in parentheses. It's not the subtraction sign. So find your negative sign key. Then you need to find the log key in your calculator. in this TI-30X IIS calculator. It's in the upper left corner, just below the second function key. log, it's the logarithmic function base 10. Don't use the ln or natural log. It's not the correct one. You want to see log. This opens parentheses. Then you need to enter the concentration, and in this case it's 1 second EE key, which is in this calculator the x to the power of -1. -7, close parentheses, enter. You should obtain a value of 7. pH equals 7 when the concentration is 1 × 10⁻⁷. So the answer to this entry in your calculator should be exactly 7. If you do not get that, you need to ask for help on how to use your calculator. It is important that you know how to calculate the pH. So let's practice, and that's practice problem number 10 from your practice problem list. So what is the pH of an ammonia solution with a concentration of H3O plus of 2.7 10⁻⁻12 molar? Is the solution acidic or basic? So again, you can pause to give you time to practice that before you look at the answer. So the first step would be to enter the H3O plus concentration into the pH equation. First, I would prefer that you actually write the pH equation. And so when you know the H3O plus concentration and you want to get the pH equal negative log of H3O plus. Remember that the brackets around H3O plus mean concentration in molarity. Then you plug in the concentration value in the log function. So it's negative log of 2.7 × 10⁻⁻12. And if you do that, 2.7 × 10⁻⁻12. So the calculator answer should be 11.568636, etc. If you did not get that, you need to seek help to know how to use your calculator. So the calculator is 11.5686, etc. We need to think about how many decimal places we will keep for the pH value. Remember that it's the decimal places only that matter. And we should keep as many decimal places as we have sig figs in the concentration. The concentration had 2 sig figs, the 2 and the 0.7. So 2 sig figs means we will keep 2 decimal places to the right of the decimal point. So 11.56568, what we keep the 5, the 6, but the 6, what comes after the 6 is an 8, so we round it up and it becomes 5.7. So pH is equal to 11.57 in this case. Is the solution acidic or basic? When you want to answer that question, you can look at the pH because that's an easier way to decide. pH is above 7, so that's basic. And you can look at the concentration of H3O plus ions. It's 10⁻⁻12. That's a very, very small value for H3O plus, which tells you OH minus is very large. Therefore, it's basic. Practice problem number 11 in your list of practice problem. If H3O plus is equal to 1.2 × 10⁻⁵ molar for a solution, what is its pH? once you have the pH, you can decide if the solution is acidic or basic. Again, you can pause now before hearing the solution. So when you're given the hydronium ion concentration and you're looking for the pH, you want to use the formula that says pH equals negative log of H3O plus. Then you plug in the value for the concentration, negative log of 1.2 times 10 to the negative 5. You enter that in your calculator, 1.2 times 10 to the negative 5. And the calculator answer in this case is 4.9208, etc. Again, you need to think of how many decimal places you will keep for the pH. And so for this, look at the number of sig figs in the concentration. The concentration has 2 digits, 2 sig figs. So you want to keep 2 decimal in the pH. So 4.92, you keep the 4.92. What comes after is a 0, so you drop everything, and it's 4.92. 2 decimal places. So the question is this acidic or basic? By looking at the pH, it's below 7, so it's acidic. Next practice problem, number 12. Calculate the pH from the following H3O plus concentrations. You have 2 concentrations. Again, pause before you see the answer. You use the same formula that says pH equals negative log of, so here the value has been changed from normal notation into scientific notation. So notice that when it's in scientific notation, it helps to visualize how many sig figs you have in this number. Remember that the 0.00, the first 3 zeros are not significant. You start counting when you see the first non-zero digit, so the 2, and then the 0 that comes after is significant. So 2 significant figures here. The calculator answer is 2.69897, etc. So you need to keep 2 sig figs. Sorry, the concentration has 2 sig figs, and we need to keep 2 decimal places for the pH. 2 decimal places means you write 2 point, then it comes 6, 9, 8. 6 and 9 need to be kept, but what comes after the 9 is a 8. So that means you need to round up. And when you round up 69, it becomes 70. Here, make sure you write the 0 after the 7, because you need 2 decimal places. By the way, pH has no unit. I didn't say that earlier, but there's no unit for pH. Let's do the next one with a concentration of 0.25. The calculator answer is 0.60205, etc. How many sig figs do we have in the concentration? 2, the 2 and the 5. 2 sig figs means we will keep 2 decimal places, and so 0.602. We will keep the 6, the 0. What comes after is a 2, so we drop it and keep 0.60. And by the way, is this acidic or basic? A pH of 0.60. This is very acidic, right? And our previous solution was also acidic because pH was below 7. So pH is below 7 in both cases. So we have 2 acidic solutions here. Notice how the 0.25 molar has been changed into scientific notation also. And you don't have to do that. You can type the 0.25 in your log directly and it will give you the same answer. You can verify that. There's no need for scientific notation. Here it was just to show the number of significant figures more clearly. So now we know how to calculate the pH knowing the hydronium ion concentration, but sometimes you will be given the pH and you want to calculate the hydronium ion concentration. The inverse formula of pH equals negative log of H3 or plus is to take the antilog of the negative pH and that translate into 10 to the negative pH because the logarithmic function is base 10. So that's why the inverse function is 10 to the power negative pH. And so for us, a pH that is equal to 3.0, for example, if you want to calculate the hydronium ion concentration, you take 10 to the power of negative pH. That's the formula. Next, you plug in the value, so 10 to the negative 3.0. And 10 to the negative 3.0 in scientific notation is written as 1 times 10 to the negative 3. Sometimes the 1 is even omitted because it's implied when it's only 1. And sometimes it just says 10 to the negative 3 molar. So here, pH was unitless. However, the concentrations have a unit. And here the brackets mean concentration in molarity. So you need the unit of capital M to say that it's 1 10 to the negative 3 molar. So when the pH is a whole number, 1, 2, 5, 7, and you take 10 to the negative that number, it's easy to calculate the concentration. It's just the pH becomes the negative exponent for your concentration. However, when pH values are not whole number, which is often the case, it has decimal, the inverse log or the 10 to the x key on your calculator can be used. So the inverse log corresponds to the 10 to the x function. Mathematically, that's the inverse function of the logarithmic function. So let's look at how we enter that in your TI-30X IIS calculator if you have one. If you have another calculator, you need to find the inverse log function or 10 to the x. Some calculator will show 10 with the exponent x, and that's the one you will want to use for that formula. So antilog of negative 4.8 is written as 10 to the power negative 4.8. So go ahead and enter that in your calculator. So in the TI-30X IIS, you need to do the second function of the log key, and the second function of the log key shows 10, the power symbol, and open the parentheses. Then you need the negative sign because it's negative pH that you need to input. Enter 4.8 equals. So if your calculator is in normal mode, it will be, the display will show 0.0000, so 4 zeros after the decimal point, I mean. So 4 0 after the decimal point, then 15849. Flips your display mode to scientific. So in this calculator, it's going to be second DRG, which is the second function of the DRG, degree key above says scientific engineering. Then with the arrow, you flip between flow to SCI, scientific, enter. And now you see the same value, but in scientific notation. And you have the little SCI at the bottom of the screen that indicates that your calculator is displaying in scientific notation. And so the answer is 1.584893, 10 to the negative 5. If you did not get that, you need to ask for help on how to use your calculator to calculate the inverse log of the negative pH. It's important to know how to do this. Again, the answer for this antilog of negative 4.8 is 1.584893, 10 to the negative 5. So let's practice using the calculator to calculate pH of, no, not calculate pH, to calculate concentration of H3O+, given the pH is 8.50 in this case. That's practice problem number 13 in your list of practice problem. Again, you can pause now before I give the answer. So what is the concentration of hydronium ion given the pH is 8.50? So here you use the formula that says concentration of H3O plus is 10 to the negative pH. Next, you plug in the value of the pH. It's negative 8.50. And when you do that in your calculator, the calculator answer is 3.162277, etc., 10 to the negative 9. You need to remember to pay attention to the number of decimal places in the pH that is given. And here it's 2 decimal places, which means you will need to keep 2 sig figs in the concentration. 2 sig figs coming from 3.16, you will keep the 1, but what comes after is a 6, so you need to round up, and it's becoming a 2. 3.2 times 10 to the negative 9 molar. Remember that it's a concentration, and so you need the capital M to show the unit of the concentration. So is this an acidic or basic solution? So you can use the pH. I think it's easier to use the pH. pH is above 7, which means it's basic. And you can also look at the concentration of H3O plus and see that if the concentration of H3O plus is smaller than 1 10 to the negative 7, which is the case here because we have 10 to the negative 9, which means it's smaller than 1 10 to the negative 7. If the hydronium ion concentration is less than 1 10 to the negative 7, that means the OH minus concentration will be more. And when we have more hydroxide ion, we have a basic solution. Some more practice. That's practice problem 14 in your list of practice problems. Determine the concentration of H3O plus for each of the following: pH 4.75, pH 12.33, and pH 0.7. Again, you can pause before you hear the answer. So here we want to calculate the concentration of H3O plus given the pH. It's going to be the formula that says H3O plus equals 10 to the negative pH. In the first case, H3O plus equals 10 to the negative 4.75. And when you enter that in your calculator, the calculator answer is 1.778279, etc., times 10 to the negative 5. You need to look at the number of decimal places in the pH. Here it's 2 decimal places, the 7 and the 5. 2 decimal place in the pH, translate into 2 sig figs in the concentration. So 1.77, you keep the 1 and the 7. What comes after the 7 is another 7, so you need to round up. So the 7 becomes an 8, and it's 1.8, 2 sig figs, times 10 to the negative 5 molar. Don't forget the capital M, which is the unit for molarity. Is this acidic or basic? pH 4.75 is acidic. And pH 12.33. The formula is again H3O plus equals 10 to the negative pH. Here 10 to the negative 12.33. The calculator answer is 4.67735, 10 to the negative 13. So we need to look at the number of decimal places in the pH. 33 is 2 decimal places in the pH. That translates into 2 sig figs in the concentration. So 4.67, you keep the 6, it will be rounded up because what comes after is a 7. So the 6 becomes a 7. And so 4.7, that's 2 sig figs, times 10 to the negative 13 molar. It's important to not forget to report the exponential part of your numbers when the calculator is in a scientific mode. Sometimes people omit to report the times 10 and then the exponent, and that changes completely the value. So make sure you look at the right side of your screen to see if there is times 10 to the power of an exponent. Is this an acidic or basic solution? When pH is 12.33, that's a pH above 7. Above 7 means it's basic. Now pH 0.7, again the formula is H3O plus equals 10 to the negative pH, so 10 to the negative 0.7. The calculator answer is 1.995262, etc., times 10 to the negative 1. So for this, you could flip to the normal mode in your scientific calculator. In normal mode, it's 0.19952, and there is no times 10 to the power. So again, we need to think decimal places for the pH. We have only 1 decimal place in the pH here. 1 decimal place means we will keep 1 sig fig only for the concentration. 1 sig fig, and if you have 0.19, you keep the 1. What comes after the 1 is a 9, so you need to round up, so the 1 becomes a 2. And so 0.2 molar. In scientific notation, this would be written as 2 times 10 to the negative 1 molar. So don't forget to write the unit of your concentrations, capital M for molarity. Is this solution acidic or basic? pH 0.7 is very acidic because it's below 7, right? Well below 7, almost 0. So very acidic.